All right, so in this problem, I'm actually going to solve every single capacitor here for its voltage and its charge. And I want to review just a couple of facts right now that I'm going to write here at the top. You should have these in your formula sheet, and I just want to be clear that when we have capacitors in series, the formulas I can look up, but I want to just kind of talk about a couple of things. The thing you should know is that for two capacitors in series, their combined voltage is that you add them up for the voltages. However, for their equivalent capacitance, you actually end up here for their charge. The charge is actually equal between the two capacitors. Now, when you have capacitors in parallel, it turns out that the voltages match their combined total. That's shared. But then it turns out that the total charge is the combination of charges on the two capacitors. I'm going to be making extensive use of these four facts when I solve this problem. So they're in your formula sheet. Please take note that I will be using these a lot. So first we want to find the equivalent capacitance. And what I'm going to do is I'm going to number these capacitors 1, 2, 3, and 4. And I'm going to begin by combining capacitors 3 and 4 in series. So C34 is going to be C3 plus C4, which is going to be 3 microfarads. And so when I write, I'm going to redraw the circuit right here. You should redraw your circuits. Don't try to be a hero and not do that because it's really going to be key for solving these problems. So now I have C34 equal to 3 microfarads, and I have C1 and C2 here, and then I have my 40-volt battery right here. Now I'm going to combine C1 and C2 in series. So that's I'm going to use the combination C12 equals C1 C2 over C1 plus C2. That's going to end up being 36 over 12, which gives me 3 microfarads. So I can redraw my circuit here now as a 40-volt battery. I'm going to have two capacitors here combined. So now I'm going to end up getting, let me smooth this up a little bit. I'm going to end up getting a capacitance at the top, C34, which we solved above as 3 microfarads. And then I'm going to have this capacitor here, C12, which is also 3 microfarads. So it's going to be a bit awkward drawing this line. All right, now what I'm going to do is I'm going to combine the capacitors into their equivalent. I can finally add C34 and C12 in series. In parallel, it's going to give me 6 microfarads. So when I draw the final result, what I'm going to end up getting is a C total of 6 microfarads hooked up to a 40-volt battery. Okay. So that is the total voltage and the total capacitance. Now, I'm going to get the charge on every single capacitor, and this is where I use the rules. Okay. So first, let me get Q total. Okay, so here I am at, I'll call this stage 3, stage 2, and stage 1. I'm going to work in stage 3 and get Q total. And the way I'm going to get Q total is I have Q total over V total is C total. Now, I know C total is 6 microfarads. And I know that V total is 40 because it has the battery's voltage. Remember, when we charge up a capacitor, if it's a single capacitor in a circuit, it will charge until its voltage matches the battery's charge. That's something that we actually did in the little mini lab a couple days ago. And so when I get Q total, that's going to be 40 times 6, which is going to end up being 240 microcoulombs. Awesome. That, to be clear, by the way, the equivalent capacitance, I would actually write 6 microfarads here. Now, this 240 microcoulombs solves nothing. I want to be clear. It is a necessary step that I'm going to use to either check my work or to do other stuff later. Now here, I'm going to work backwards to capacitors 3 and 4. Now, the rule with capacitors 3 and 4, they are in parallel with each other. What does that mean? The rule is that when capacitors are in parallel, they say they share the same voltage, and that voltage will actually match the battery that they're connected to below. What that means is that I'm going to have a 40 volts on this capacitor and 40 volts on this capacitor for C34 and C12. Working with that, you know what? I didn't write that. I want to write this as V34 and 40 volts as V12 right here. So continuing with that idea, Q34 over V34 equals C34. That means the charge on capacitor 34, I'm going to actually continue this here. The charge on capacitor 34 is going to be given by Q34 equals, well, I've got the 40 volts on it using the parallel rule, times its capacitance, which is 3. That's going to give me 120 microfarads. By a similar calculation, similarly, Q12 is going to equal 120 microfarads. So, I'm going to get Q12 as 120 microfarads and Q34 as 120 microfarads, each with a voltage of 40 volts. Now, why do we care? Well, am I working the right way? Let's just do a little check here. So for capacitors in parallel, the total charge is the sum of the two charges on each capacitor. So I had a total charge of 240 microcoulombs. Sorry, this is microcoulombs here, not microfarads. When I add these up, 120 plus 120 is 240. So I'm maintaining my totals. That's a good indication that my math is on the right track and that I'm doing things correctly. All right, now we're finally ready to start breaking things down. So here we go. I can say for certain that C34, I'm going to get V34, I'm going to work here. So I can say for certain that the voltage on this capacitor is 40 volts because it's in parallel with the battery, because that stays unchanged. Now we have a little issue here, which is that I have 120 microcoulombs on C12. I need the rule for series capacitors. I'm taking this and I'm breaking it into its series components. So I go to the series rule and I realize, aha, they share each the same charge. So I'm going to start with the idea. I'll underline it here in orange. Right here. And then I'm going to actually use that fact here. So I'm going to have 120 microcoulombs here and 120 microcoulombs here. And I have each capacitor has a capacitance of 6 microfarads. 6 microfarads. So now I can get Q2 over V2 equals C2. I know the charge. Now I'm going to get the voltage on this capacitor. So I'm finally solving something useful. So I get that V2 ends up being Q2 over C2 when I do my algebra. That's going to be 120 over 6. That's giving me 20 volts. So I'm getting 20 volts on V2. Similarly, V1 is going to be 20 volts. So let's kind of label what we have. We finally got ourselves one useful set of data. So I'm getting that C1, V1, and Q1 here can be written as the following. C1 is 6 microfarads, V on 1 is 20 volts, and its charge is 120 microcoulombs. Similarly with, you know what, that's not what I want to say. So I have what the capacitor is, what its voltage is, and what its charge is. So this is capacitor number 1. So capacitor, sorry, 9/millionth times the charm. The capacitor number, its value, its capacitor number, its C value, its V value, its Q value, all laid out here. So capacitor number 1, 2, 3, and 4. Capacitor 1 has a capacitance of 6 microfarads, and we got that its its charge was 120 microfarads. So we got that its voltage was 20. Similar for capacitor number 2, 6 microfarads, 20 volts, 120 microcoulombs of charge. This is microcoulombs. Sorry about that. Now, for number 3, we're finally ready to go into the beginning here. So I have C34. It's in parallel. So what does that mean? That means I have here 40 volts and 40 volts. And I have 2 microfarads. So for C4, I know that C4 is Q4 over V4. And I know that I have 40 volts. Let's keep going. So I have 2 equals Q4 over 40. That means Q4 is 80 microcoulombs. And here for Q3, I'm going to get C3 is Q3 over V3. That's going to be 1 equals Q3, unknown, over V3, which is 40. I'm getting 40 microcoulombs for Q3. So let's kind of lay it all out. So C3 is 1 microfarad, and C4 is 2 microfarads. I'm getting 40 volts on each, and I'm getting a charge of 40 microcoulombs and 80 microcoulombs here. So I just got the charge and the voltage on each capacitor. Notice I had to kind of work on both at the same time. So these two parts will always be combined. Now, if I wanted the energy on each capacitor, let's just do that now. Okay, so that's going to be 1/2 of Q times V. So that's going to be 1/2 of 20 times 120 times 10 to the negative 6th. And when I actually work that math out, let's just do that now. Okay. So here we go. Whoops. So 20 times 120 times 10 to the negative 6th divided by 2. That's giving me 0.0012 joules. Similar, I'm getting 0.0012 joules here. Now let's get this one here. This ends up being, when I get it, 0.0008 and 0.00. Let me just make sure I got that right. So now let's see. So 40 times 40. Yep. 0.0008. And then 40 times 80. Yep. 0.0016 joules. All right, so that's the energy stored on each capacitor. Again, I was using the formula 1/2 QV. Any of these would actually work. So that is, in fact, the first part of your first problem on your practice exam. I'll put that video up now.